In 5, 4, 3, 2, 1.
Great. Let's see. All right. So good morning, good afternoon. Thank you all for joining us. My name is River Bennett. I am a graduate researcher at the National Reactor Innovation Center, and I am very excited for today's Tech Talk. It's an easy slip, because this is a topic I've been interested in for at least the last couple of years. And so I've been excited to work with some of the people on this call, and I'm excited to talk to you all some more about this very exciting topic for advanced reactors in the maritime industry. So just to give a kind of an overview on the topic, nuclear power was first developed for use by the US Navy at sea. And we think that today advanced reactors provide the opportunity to take that technology and use it for a pretty broad range of commercial applications in the maritime industry. So for non-military applications that include propulsion and kind of a whole bunch of other very interesting kind of niche markets. And today we have maritime professionals and advanced reactor vendors who are going to have the opportunity to learn more about each other's industries, both the market opportunities for advanced reactors and the technical progress that are being made by vendors. So next slide, please. Great. So for those in the audience who would like to participate, for the best experience, we recommend turning off any VPN connections. We're going to have a Q&A session at the end. So if you have any questions, there's a Q&A button where you can submit those, and we'll make sure to address them kind of in the order that they come in. If you have any technical problems, please put those in the Q&A as well. If you have any programmatic questions, you can email us at nric@inl.gov. And most importantly, this event is being recorded and it's going to be posted on the NRIC website. So your attendance is consent to that recording. Next slide. So a little background on NRIC. For those who are not familiar with our program, the National Reactor Innovation Center is a Department of Energy Nuclear Energy Office Center. We were launched in fiscal year 2020, and we have a few kind of key aspects in our mission. So we were authorized by the Nuclear Energy Innovation Capabilities Act, also known as NECA. And we focus on, we partner with industry to bridge the gap between research and commercial deployment of advanced reactor technologies. In order to do this, we leverage the national lab expertise and infrastructure throughout the US, and we manage demonstrations all the way through to success. Next slide. And our vision for this effort is to have at least 2 advanced reactor demonstrations by the end of 2025. So we're coming up on that, and it's been a very exciting time so far. Next slide. And in order to achieve these goals, we are driven by our mission, which is to inspire stakeholders and the public, empower innovators, and deliver successful outcomes. Next slide. And most importantly, in order to achieve all these goals, we put collaboration at our core. So we do not do this by ourselves. We work with a very large group of stakeholders in industry, in government, as we'll discuss today, across different industries. So not just in our own kind of nuclear space. And just in this graphic, you can see kind of a small example of some of the different organizations that we work with in order to achieve these goals. So it's really a national effort, and as well as a regional and local effort. And yeah, we'll get into that some more today. Next slide. Great. So today we have, I'm joined here today by 3 speakers who I'm very excited to introduce. And the way this is going to work is I'll introduce them very briefly right now, and then I'll go into a little bit longer bio for each one before they give their presentation. So they're kind of ordered here in the order that they're going to be presenting. So I'll start with Meg Dowling, who is the nuclear programs lead engineer for American Bureau of Shipping. Meg and I work together a lot. We do a lot of work together. We've been working on a joint American Bureau of Shipping and National Reactor Innovation Center our research project that's somewhere about a third of the way through. So we've been learning a lot from each other. So I'm excited to have her join us today. Meg joined ABS in 2019 as an Aspire rotational engineer, where she gained company-wide experience with marine classification, sustainability projects, transfer of class, risk-based inspection, alternative fuels, offshore structures, and mooring arrangements. She now works on subjects related to sustainable shipping initiatives and alternative power options such as hydrogen fuel and nuclear power. Meg received her BS in Ocean and Naval Architectural Engineering from the Memorial University of Newfoundland in 2019. Her time in that program included 5 work terms related to maritime regulations, engineering design, ship refit and modifications, shipyard activities, condition monitoring, and vessel life extensions. So Meg, I'm going to let you take it from here. And next slide.
Thank you, River. Thanks to everyone for joining today's Tech Talk. I'm excited to share a different perspective here. And you can jump to the next slide for me, please. So River already introduced most of what I was going to say about myself, but if you're not aware of what the American Bureau of Shipping is, I'd like to give a short introduction of how we fit in to that industry. So we are a classification society, most associated with activities in the United States. However, ABS is also located globally with over 5,000 personnel worldwide. Most of those are surveyors attending ships and vessels in ports around the world. Our mission is to serve the public interest as well as the needs of our clients by promoting the security of life, property, and natural environment with safety at our core for the marine activities. Our primary function here is to establish and apply technical standards for the design, construction, and survey of ships and offshore structures. And we establish those standards through various research and industry engagement activities to develop new safety protocols and test and practices for marine assets. We apply these standards through our engineering review and advisory services, but enforce them with verification and certification activities, as I mentioned, through our surveyors who are deployed globally. So I play a role in the research and development department, corporate headquarters in Houston, Texas, doing lots of research on alternative fuels, as River mentioned. Next slide, please. A little bit more about classification and how we fit in here. We have a unique position where we see a ship from its design and concepts all the way through to classification. We work with the machinery and structures on those vessels, and we also carry through with that vessel until its end of life as an ABS class vessel. So only class societies can class ships and marine structures, while the machinery and equipment certificates on those ships may be issued by class or any other recognized organization. So we're really focusing on the ship itself, requires classification in order to travel internationally. So ABS plays one of many stakeholder roles for marine assets, including those, we interact with all stakeholders, and we do that with safety at our core to make sure that everyone's on board with the design, the operation, and the end of life activities. So as we start kind of considering how to merge maritime with nuclear activities, that will also include reactor licensors, designers, and manufacturers for reactor technologies. Next slide, please. So what is ABS's experience and ongoing activity with nuclear for maritime? It started actually in the 50s and 60s. We were heavily involved with maritime associations discussing how to put nuclear power at the time with the Eisenhower Atoms for Peace initiative. Everyone was really excited about showcasing nuclear on commercial vessels. So we classed the nuclear ship Savannah in 1961, which operated for about a decade. And we did that using the rules, ABS rules for nuclear vessels. And we continue actually to class this vessel as it sits in Baltimore Harbor. Even though the reactor is decommissioned, it's no longer an active vessel. She's still floating, and we still have active engagement with her in Baltimore. So this sets our precedent of historical records and showcases a safe operating record. At the same time as it helps us provide lessons learned about the commercial nuclear activity throughout the years, starting in the 60s. And those lessons learned, we can move forward, especially, for example, regarding decommissioning of that project. And we need to think about the life cycle of an asset. And ABS is, that's a regular activity that ABS does, is not only the construction, design, and operating commissioning, but also decommissioning and end-of-life activities. So next, primarily, ABS provides other supporting services for clients, where we publish rules, guidance, advisories, insights, and other public documents to advise interested industries on important and upcoming technologies or practices. So that's us speaking to our clients and the stakeholders in the maritime or any other industry to show what we're doing to meet international maritime goals and how to address new technologies. We also offer new technology qualification services for equipment that may not have appropriate marine standards or may not have extensive operating experience in marine environments. Results of this work have led to equipment statements on technology readiness or maturity. So that's individual pieces of equipment that are to be installed on marine vessels or offshore assets. In addition to that, we also carry out concept and feasibility studies for novel concepts. So that's actually the entire vessel associated with new technology and how the unique arrangements can be approved and how we can safely install them for classification and readiness for operation. So a lot of that work for concept and feasibility studies is directed at investors and other stakeholders who are interested in understanding how feasible a new design may be. So ABS is involved in providing those concept assessments. We also have a private subsidiary known as ABS Group, who provides consultancy services with a track record of experience, many years focusing on land-based nuclear plant safety and the risk studies associated with nuclear on land, which we can leverage for marine nuclear concepts in the future. And finally, a lot of the work that I'm involved in my department is with industry and academic partners for collaborative projects, advancing the understanding of this technical opportunity and the challenges that we may face technologically as well as regulatory challenges. So that means we engage with government agencies, with other standards organizations, scientific institutes like the INL and NRIC, and other universities as well globally, not only just in the United States, to produce comprehensive research and development solutions. So my office in Houston is doing a lot of this work, but we also have a big research center in Singapore, in Korea, and Athens, and a lot of work's done in London and Copenhagen as well on various marine technological activities. One of these partnerships includes the Maritime and Nuclear Applications Group, MNAG, which is a put together, I guess, by ABS and NRIC and a law firm to discuss and bring these stakeholders together to show how nuclear and maritime can operate, can work with that important input from both sides of the industry. So moving on to the next slide, I want to talk a little bit about some of the specific award projects and research that I'm working on. As River mentioned, I am working with NRIC based on this award that was notified or announced a year ago. We started 2 years ago, actually in 2021, and we started in July of 2022. This award is focusing on investigating the regulatory roadmap to achieve maritime nuclear applications in the United States. So we're specifically directing this research to advise the DOE and supporting research for nuclear maritime applications, primarily for decarbonization goals. That's why there's a big push for this right now, and also sustainability goals. So this research, we're going to be looking at all kinds of maritime applications. How can nuclear benefit the maritime, not only the US maritime industry, but also global maritime industry, decarbonization goals in the future. So let's see what those look like. If you can jump to the next slide. And I'll just insert another project that I'm involved with. Some of this research funding from the DOE is also interacting with universities. So there's another project with the University of Texas, Dallas. Their research is more technically driven, and they're looking at the integration of thermal electric systems for marine propulsion. So that research goes until 2025, and ABS is supporting that from a marine classification perspective as well. So moving on. This slide is kind of just summarizing everything that we're trying to cover, right? We're looking not only at vessel propulsion, where when we first mention maritime nuclear applications, the first thing that probably comes to mind is, well, we've been doing it for the navies for a long time. We might as well just switch that technology and make it commercial. While that sounds easy and beneficial for the decarbonization of a maritime industry, it's probably not as simple as we'd like it to be due to regulatory constraints. Transporting nuclear, just having any concept of nuclear transportation is difficult for everyone and all the nuclear agencies to wrap their head around. And you're not really meant to read this chart in the bottom left, but it's from a report from the International Maritime Organization. They did a greenhouse gas study a couple of years ago, reporting on how much greenhouse gas is emitted from international shipping. And this chart you can see on the left is very high in categories of very large ships. So the meaning of that is the largest ships emit the most greenhouse gases and pollutants in the ocean. So those are the ones that if we were to talk about nuclear as propelling vessels, we would probably target those large vessels. I think we'll hear more about that later in this presentation. But we're also looking at the offshore industry. It probably will be easier to regulate if it's stationary, if it's near shore. You can install nuclear power for various offshore industry activities. So that could be nearshore power. It could be for any kind of aquaculture installation if power is required, leveling, offshore wind power, offshore energies. And I know it's kind of an oxymoron to say to decarbonize the oil industry, but oil industry is still, they still need to decarbonize, and we will still continue to need hydrocarbons. So we can't just stop that activity. Might as well help decarbonize that industry as well. And then I guess my main point is if anything needs power, if the maritime industry requires a large amount of power and not a lot of space to do it, we should consider that the possibility of installing nuclear power on those assets to provide that decarbonized, sustainable power solution. Although there will be challenges, the technological solution and technological answers, I think, will probably be solved first. And talking about them is what we will get to address the regulatory gaps. I think that's my last slide there, River. Yeah, thank you for your time and listening to my quick introduction, and I look forward to the questions that you have.
Excellent. All right. Thank you, Meg. Yeah, so we can go to the next. Yeah, just this slide right here is perfect, right? So I'm going to introduce our second speaker today. This is Arnav Sengupta. He's a managing director for Anglo-Eastern Technical Services. And Arnav joined the shipbuilding and special projects team at Anglo-Eastern Group after 14 years experience at sea as a marine engineer. As a managing director of Anglo-Eastern Technical Services, Arnav has undertaken several prototype shipbuilding and ship retrofit projects over the years. He has guided his team in developing 3 distinctly different ammonia dual fuel ship designs and currently oversees several projects aimed at reducing emissions from existing ships. The ship new building programs presently under his charge are highly energy efficient and several designed to use alternative fuels such as LPG, LNG, methanol, and ammonia. So Arnav, you can take it from here. I think your presentation starts on the next slide. Oh, you're on mute.
Thank you, River.
Okay, great. We can hear you now.
Good day, ladies and it's okay now?
Yep.
Okay. Good day, ladies and gentlemen. I represent Anglo-Eastern, a company that has 680 ships under its technical management, which is approximately 6% of the total number of ships under third-party management globally. As technical managers, it is our responsibility to not only take care of the multi-million-dollar assets that our shipowner partner trusts us with, but also to advise our partners on future assets. This means that we must guide our partners on technology that would comply with future regulations. Next slide, please. Ship engines burn enormous amount of fuel, and today a fat finger points at the industry as we continue to emit large quantities of greenhouse gases. Of course, some of the emission is from the production process, and thus the wake to well outlook is important. This slide picks from a study by Class NK and provides an interesting overview of greenhouse gas emission for all known fuel types, and also makes a quick comparison with some possible future fuels. If we take the number seriously, then obviously we will all agree that there is an urgent need to shift away from the fossil fuels. But the question is, how soon would that be possible? Next slide, please. This slide provides a projected roadmap on regulatory reduction of emission from ships. The 2020 and 2025 figures are actual mandated reductions. The ones for the future are projected based on industry indicators. This is actually a good start point as it can convey the urgency with which the shift from fossil fuel is necessary. The critical transition period will start soon, but the preparation for the transition must commence now. Next slide, please. If we compare the GHG emission from known fuels and the projected reduction criteria, it is quite evident that even LNG or LPG as fuel will not remain dependable beyond 2035. This means starting 2030, ships capable of burning clean fuel must be on water. The next decade would be interesting, as it will indeed be a decade of critical transition in the shipping industry. Next slide, please. A ship normally has a 20-year life cycle, meaning those on order must trade beyond 2045, and those under construction now must comply with the mandatory regulations of EEDI Phase 3 and NOx Tier 3. But for a ship delivered today to trade up to 2045, a midlife retrofit would be required. We at Anglo Eastern have developed designs for ammonia dual fuel ships and secured approval from classification societies, LR and ABS. One of our partners, CMB, liked the design and the concept and acted as a first mover, and now we have 32 ships under construction that would be delivered ammonia ready, and another 6 units that are expected to be delivered fitted with ammonia dual fuel engines. Of the 32 ships, 28 are being built under class ABS. Next slide, please. We think ammonia and methanol, the green ones, not the ones produced with the energy from the black stuff, the e-ammonia and e-methanol will become and remain important transitional fuels leading to 2050 or probably even up to 2070. But the big question is, do we have a known source of sustainable energy to produce the green fuel? 60,000 ships are in service to meet global trade requirements. This means retrofitting or replacing existing tonnage to eventually getting to zero. Next slide, please. Frankly, we have ship designs, we have ships under construction, and we will have engines that will burn clean fuel. Thus, the demand for green fuel will develop and then maintain an increasing trend. But the burning question will remain as to whether we will have clean fuel. More importantly, of course, if we will have sufficient clean fuel to cater to 60,000 ships that are required to keep the world running. Do we have the energy source to produce the humongous amount of clean fuel required? Fortunately, here, the answer in this case is a big yes. Yes, it is possible, but only if we avail nuclear energy, which is the only sustainable source of clean energy. Next slide, please. I think that's it. With this thought, ladies and gentlemen, I pass it on to the next speaker, who knows a thing or two on how clean energy can be produced. Thank you.
Excellent. Thank you, Arnava. Before we move on to our last speaker, I'm going to introduce him. So Yanis Kourasis graduated from the National Technical University of Athens with a master's in applied physics and mathematics, specializing in nuclear physics and advanced materials. He works as a nuclear engineer for Core Power, with a focus on nuclear safety, security, and the regulation aspects of implementing nuclear in commercial marine applications. All right, thank you, Yanis.
Yeah, thank you very much, River, for the introduction, and greetings from London, everyone. I'm happy to see everyone joining. So today I'm going to discuss advanced nuclear applications at sea, and the previous presenter greatly alluded to nuclear propulsion and nuclear production of e-fuels. So I'm actually going to show you two applications that do exactly that, spoiler. So first, if we move on to the next slide, I'm going to quickly introduce our company in case you're not familiar with it. So the company basically co-develops and finances advanced reactors, specifically to be used in the future for marine applications. At the same time, of course, we are engineering and designing these solutions. To do all that, we are partnered with nuclear developing companies like TerraPower in the US and nuclear operators like Southern Company. So, as I said, I have two exciting applications to show you, but to get to a successful application, if we move on to the next slide, so to get to a successful application, you need to choose the right reactor. And actually, I saw just today that the first bullet point of the whole tech talk by River was that naval reactors have operated at sea, of course, safely for many decades. And we are looking to advanced reactors for maritime applications. And the natural question is why? Why don't we just use the naval reactors? And this slide basically tries to answer that. So we have identified three key criteria for that reactors have to meet to be fit for purpose for commercial maritime use. And I will go over why we need each one. So the first one is a very long fuel cycle. This is for economic feasibility reasons. The longer the fuel cycle is, ideally with no stops for refueling for the entirety of the lifetime of the application, the lower the operation cost, the OPEX, is. Also, the long fuel cycle solves the safety consideration of fuel handling on board, which is very important. The second one is we need reactors that have components that can be manufactured in a mass assembly line, mass manufactured, to increase the production scale and to take it to a place where many multiple modules can be produced cheap and fast, and of course safely, which comes in great antithesis, let's say, to current land-based projects, which are big one-off projects. And I think this is the narrative for small modular reactor designs. And the last one is, and Meg alluded to this when she mentioned regulation, the last one is we need a reactor with a small emergency planning zone, ideally to the boundary of the application, reduced to the boundary of the application. And this is for easy access to ports and canals that don't require thousands of people to prepare for emergency, and also for liability reasons that I won't go into today. So we have identified three reactor technologies. So that is I believe that many perceptive people in the audience will have realized that naval PWRs do not fit this criteria, and that is why we need to look at advanced reactor technology for commercial maritime applications. So we have identified 3 reactor designs that fit this criteria. And today I'm going to discuss the one that we are actively involved in developing. So if we go on the next slide, please. Yeah, so this reactor is the molten chloride fast reactor. This is a pool type molten salt reactor. And I want to explain simply because I know we have maritime people in the audience and also in the panel. So this reactor has the primary coolant and the fuel mixed together in a single homogeneous salt, basically, which liquefies at temperatures over 450 to actually 525, depending on the composition. Yeah, so think of it as a liquid that goes critical and produces heat through the fission reactions. And then to extract that heat, we circulate the molten salt through heat exchangers that are inside the reactor vessel in a closed loop. The temperature of this salt can go very high, and that is a very nice benefit because we have increased thermal efficiency. And as you can see, it is a fast reactor, so the neutron energies are high. We don't have a lot of moderation, and this allows us to have the extremely long fuel cycle that I showed in the previous slide. And also it gives us many other benefits that I can get into during the Q&A if someone is curious. And lastly, it operates at almost ambient pressure, which is very nice because it greatly reduces the probability and severity of many accident categories that we have in nuclear, which allows us to start doing work on making the argument and providing the evidence to support that the dose in the case of an accident outside of the ship will not require emergency response, and this is how you reduce the EPZ. You have to prove it safe enough, basically. Now, when it comes to power rating, as with many SMR designs, those in the nuclear space will know this, we have a variety of power ratings. The one that is closer to us, it is a demonstrator, which goes up to hopefully in 2030s and goes up to 180 megawatt thermal. And we hope to have this demonstrator in a marine environment, which will, let's say, open the door for our applications. So if we go on the next slide. So our first application is nuclear electric ships. So this is converting the energy from the reactor to electrical energy, making electricity, and then using that electricity to power the ship. So propulsion, the hotel load, and also you can power the port when the ship is at port using reverse cold ironing. I want to make a very important distinction here. So this is not a one-size-fits-all solution. So we accept that one part of the commercial vessel will have to use, it's better suitable to use green e-fuels as Arunava mentioned. However, this targets the larger types of vessels, which have the biggest piece of the pie when it comes to carbon CO2 emissions, which Arunava showed in his graphs. Here I have an example of a concept design of one of our concept designs. This actually has a very large in its name, so it's a very large ore carrier, VLOC. It's 390,000 deadweight tons. And using this specific design, this specific vessel would operate with 0 emissions, with 0 stops for refueling. Then this is for 25 to 30 years of its lifetime, of the reactor lifetime. And it could go up to speeds up to 20 knots, which is very fast and actually a benefit that many people miss. So when it comes to decarbonizing and shipping, usually you see solutions that tell you to go slower to reduce emissions. With nuclear, you can go faster with 0 emissions, and that greatly improves the profit margins. This is where we believe it's a very disruptive solution. On the right, you can see a section of the concept design. and you can spot some of the engineering work we are doing currently. For example, the shielding. We have to add an extra layer to make the dough slow enough outside of the ship to reduce the EPZ and to protect the crew of the vessel. So if we go to the next slide, we have, as I promised, the second application, which is floating power plant. So the good thing about small modular reactors is that you can install multiple of them. And doing that, we have created this power plant, which goes up to 1.2 gigawatt electric output. And we have calculated that it is about 50% cheaper to construct this floating power plant than to construct the same power plant at land. The equivalent, let's say, not same, the equivalent power plant at land. And that is because of two main reasons. The first one is you have abundant free cooling around, which is the ocean, the seawater. And the second one is that you actually don't need a lot of concrete, and you replace the structure is mostly made out of steel. So you replace the big costs that come with concrete construction. The most interesting thing about this power plant, which has been spoiled by the presentations, is that it can be used not only to power the grid, but it can be used for more exciting applications, which is if we go on the next slide, which takes a while to load. Bear with us. The anticipation is building. Yeah. So yeah, this is the application. You can couple this nuclear power plant to a chemical plant. In this example, the energy from the power plant is used to produce hydrogen in the chemical plant by electrolysis. And then the hydrogen is used to synthesize green fuels, so ammonia and methanol. Here, again, you might notice that we transfer electricity, but we also transfer heat directly from the power plant because it is there is a case to be made that is more efficient and heat can directly be used for the electrolysis process. But we can get into this in the Q&A if you want more details. And we are actively working with MIT and INL on a project that is a feasibility study on this kind of coupling of chemical floating plant with, nuclear floating plant with chemical plant. And I think it is a very exciting application. And that is all I have to show. Thank you very much for listening, and looking forward to the Q&A.
Excellent. Thank you, Yannis. So we're going to move into the question portion now. We have some questions coming up, and I'm going to start with some easier ones and build up to some of the trickier ones just to get you all warmed up. So just to start, what would you say is the main driver for developing nuclear powered ships today, right? The technology has existed for a while. We've tried it in the past, we stopped doing it, but what is it about today that's, building interest in this again? Whoever wants to start, I think everyone probably has an answer.
I can have a thought on that, River, if I could start.
Yeah.
Speaking for the maritime industry, of course, the driver has been decarbonization internationally. So the International Maritime Organization itself has established greenhouse gas emission reduction targets that I think Dr. Aranava touched upon, but their goals are actually to reduce CO2 emissions from marine transport by at least 40% by 2030 and 70% by 2050, and that's just carbon emissions, and to reduce greenhouse gas emissions from shipping by 50% by 2050 from the 2008 emissions values. So that in combination with advanced nuclear, small modular reactors, potential benefits of advanced and next generation reactors are showing we can't really ignore nuclear anymore for this decarbonization problem, right? Even if we look at other alternative fuels, there's still various issues, and we really at this point, we need to look more into it, and we can't just discard it as the first option.
Absolutely.
Yeah, I can add on to that if you like. Yeah, so basically we speak with maritime engineering companies almost every week. And what they tell us is we need to find decarbonizing solutions, and actually the green fuels and e-fuels, and of course, Arunaval will know this to a much greater degree than me. Those transitions and those retrofits are not easy, are not cheap to do, and will not result in zero emissions. So the nuclear solution is a disruptive solution that will result to zero emissions, and all it takes is a 5-minute presentation to make this clear to ship owners, maritime people, and that is why I think there's a big drive, as people start to realize that there's a big drive to include nuclear in the mix. I don't know what Arunava has to say regarding that.
No, actually, you're right. So is Meg. Basically, we have to decarbonize, and to decarbonize, you require a huge amount of e-methanol and e-ammonia. I mean, probably they are the transition fuels. And what is required is the energy. We don't have. I mean, we cannot make it an unsustainable production process, and the only way is to have clean energy to produce this fuel. Till the time you have a general consensus on having nuclear batteries on board, till the time we have to have green fuel, and that is the only possibility probably is through using nuclear energy.
Yep.
Great. I guess I'll push back on that just a little bit, because I think one thing that's right when it comes to the nuclear sector in terms of what we think our markets are, we think a lot. We're probably focused mostly on land stuff, right? And what are like the kind of drivers for adopting nuclear power on land? And I think they're probably pretty similar to the maritime industry in terms of we need to decarbonize, but could you explain a little bit, what the pressure looks like on vessel owners and operators? Just explain what that means to have these, kind of imminent regulations about emissions, because I think that is something that is a bit different from how we're dealing with plants on land. And I'd be curious if you all could explain that a bit more.
I can start again, River. I think Arunava might have more accurate information to share, but so overall, the pressure is coming from international regulators and also national regulators. So if we're looking at the United States itself has transportation decarbonization goals. Internationally, like I said, the IMO is requiring these decarbonization goals and greenhouse gas reduction goals. They're doing that by tracking all vessels and all of the emissions and estimating the total emissions. So we've got emission measuring technologies that are going out there. There's a lot of effort going into capturing emissions on board ships, actually, and capturing pollutants and CO2 on board the vessel itself, as well as sulfur oxides and nitrogen oxides that are typically emitted in a combustion engine. So the IMO is enforcing this through something called a CCI, where you have to calculate the energy efficiency and the carbon output of your vessels from a fleet perspective as well as from individual vessels. So, and if that is not met, then I believe there's a system of fees or fines if you don't meet that. You'll have to just pay the fine rather than reduce your carbon emissions. And I might not be completely accurate on that because that's not my realm of expertise, but there is significant repercussions if you don't meet these decarbonization goals, not only from the, like I said, international point of view, as well as the domestic point of view. So wherever the ship is flagged and wherever it's going, there's certain areas, protected marine areas around the world, and environmental protected areas where you need to reduce your emissions in typically higher trafficked areas, near the North Sea, near Copenhagen and the north of France. That's a big environmentally protected area where ships need to turn off their heavy sulfur fuel emissions and need to transition, at least for a small amount of time while they're in that zone, to a lower carbon emissions or lower greenhouse gas emitting energy solution. I'm sure that Aranapa has more to say on the consequences of not meeting decarbonization drivers.
Yeah, Big, to just start from where you finished. The carbon tax. The biggest worry for the ship owners is the carbon tax that would be levied. It's not decided yet. The EU ETS regulations are coming in, and there is a huge fear amongst the ship owners about how much fine that they have to pay because of the carbon being emitted, the CO2 being emitted from the ships. But the problem at the same time is there is a huge amount of uncertainty. We have one of our ship owner partners who's taken a huge risk, being the first mover and investing a lot of money in preparing ships for retrofit, to the extent that they have invested in the complete structural work at the new building stage, and so that they don't have to, I mean, the layup time for retrofit and the cost of retrofit is reduced. But this is all with an assumption that green fuel would be available. It's not available today. I mean, the engines would be there. The engine makers, we discussed with the engine makers, and they're pretty confident, and by end of 2025, we will have the engines for ammonia. Methanol engines are there. Methanol dual fuel ships are being built, but we don't have green methanol. So the biggest problem is the availability of the huge amount of fuel that is required to run the 60,000 ships on water. And they will be phased. I mean, the older ships will be phased out. That's true, and the newer ships will come. But how can a ship owner take the risk of not knowing which fuel would be available? And obviously, having nuclear battery packs on board, that probably the life cycle of the ship can be increased to even 35 years, because you don't have the maintenance issues, or the normal wear and tear of the normal machinery. But the problem is that it may take some time to get a general consensus. I mean, the governments have to agree. There's a huge amount of convincing of different stakeholders is required. So that may take time, as the study report from ABS says. So, but at this time, what is required is to have green fuel, and for that, obviously, the nuclear energy would play a huge part. That's what we believe.
Great, thank you. So I said I wanted to warm you all up because the trickier questions are coming in now, and I wanted to move to those because I think one of the biggest questions around this is, okay, we can build these, right? We've proven we can do that, but where can we use these technologies, right? There's regulatory, there's international restrictions on certain technologies. So how do we navigate that? We have a good question here in the chat. We have a few, and I'll try and combine them, but this first chat, I think, or question is good for summing those up. And it says, regarding maritime regulation, what regulations would apply to nuclear systems in international waters? Would the envisioned regulatory framework have to be international in nature? Thinking of potential regulatory issues for nuclear vessels that move between national waters, for example, a vessel going from Singapore to the Netherlands.
That's a great question, River, and I can start. There are maritime international regulations for nuclear powered vessels. However, they were developed in the 1960s, they're updated in the 1980s. They do not cover the core, the actual reactor that's installed, but they are specific to pressurized water reactors, which were the only ones used during that time for maritime applications, and the regulations haven't been used since. So that's the IMO has published their International Code for the Safety of Life at Sea. That's SOLAS, Chapter 8. If you go there, it's 2 pages of goal-based requirements that a nuclear-powered vessel or ship needs to have these functional systems on board just for the basic safety of the vessel. mainly to protect the crew and the surrounding area from radioactivity. That's pretty outdated. There's an appendix to that that's about 100 pages long, a little bit more, which goes into more detail about the operational requirements and the criteria that a reactor needs to meet to be suited for suited on a marine vessel. So those two exist and you can find them online, but they're outdated and they may need to be adjusted and or updated for an advanced nuclear reactor on board a vessel. So that's already in existence. But it's not very helpful. So the second part of this question is thinking about ships that travel internationally. They will have to meet international standards. That's right. They'll have to meet whatever the IMO requires, but they'll also be subject to their flag administration. So that's wherever they are registered, they will impose engineering requirements upon that vessel to meet, and it needs to be actually done. So you can see that there actually are nuclear vessels that operate today, but they're technically not merchant vessels and they're technically run by the government. So they are meeting their own internal requirements for those vessels, for nuclear powered vessels. But for a merchant vessel, maybe in the United States going to Europe or from Singapore going to Europe, they'll probably need to meet not only the international requirements, but also the source, wherever they're coming from, requirements for the design and safety of that system, as well as the destination requirements of the port that they're going to. So there's a big challenge here about what that's going to look like and how we can address that. But I would leave off by saying, because there's so many different kinds of solutions and different types of advanced reactors that we're thinking about right now, and I would recommend first to follow all of the developments going on in land-based reactor development, because it will kind of lead us to understand which ones we can apply best fit maritime. We're looking for goal-based requirements. We're looking for functional goals that you can meet with your design, rather than prescriptive requirements for this size shielding or this specific arrangement or safety systems on board. It's up to the designer of that vessel and reactor to show that their engineering systems and their safety systems and procedures meet goal-based standards primarily, rather than prescriptive requirements. I hope that answered the question. They are under development. There's a lot of discussion about that right now to clarify, to find the gaps in the regulations and to see where we can move it and advance it to modern technology.
Great. So I think I'm gonna kind of in that same vein, I'm gonna direct this next question at Giannis, because we're getting some questions in the chat kind of about security and safety and how these will work. And I figured I would publish some of these questions and put them in the chat. So I'll give you an example of one, for example, that says, given the rise in international terrorism in the last decades, including piracy and bad actors attacking commercial ships, how will nuclear powered ships be protected from such terrorist and bad actor nation attacks? Similar to that, we have questions about proliferation. And so I'm curious if you could go into some of your thoughts about that.
Yeah, so security is an extremely important aspect that we are working on actively, even at this preconceptual stage. And I have seen also the two questions that you mentioned, which are very important to answer. So for the proliferation, we have to say that the molten salt, the specific chloride salts, and with the fast spectrum are one of the most proliferation-resistant fuels, because actinides are mixed with the lanthanides, and they have been recognized by multiple security professionals and organizations around the world. The molten salt reactors are the least likely reactors to be susceptible to things like core damage and other security threats like theft. Specifically, when it comes to core power applications, we have implemented a series of physical barriers in our design. So we have security by design. We have 8 physical barriers in case someone wanted to access the fuel. And we also have passive measures. For example, in case of piracy, the fuel is poisoned. So we have neutron poisoning material in the molten salt, and then the salt is frozen. So it is unusable, and it cannot be proliferated, it cannot be used by a bad actor to cause any amount of damage. And also, it is important to think about the state of the fuel. So this is a very high temperature, very corrosive fuel. So our argument is that for someone to be able to steal it and use it, they will have to have the equipment and engineering of either a big government or the decommissioning facility that the reactor will go to at end of life. So it's not something that you can easily handle. And it will freeze under 450 degrees. It cannot spread or create a plume or anything like that. But yeah, we take security very seriously. All our vital systems are compartmentalized and are redundant. So there's no single point vulnerability in the design, which is a very important security factor. And also what helps really with terrorism is intelligence. So you need to have the right intelligence when it comes to the routes you're taking, the routes the ship is taking, and what are the potential dangers to prepare for that and to be ready. So I hope that gives a rough idea of how we handle security and the security culture overall.
Yeah, if I could add to that, Giannis, that's a great example of how to take an advanced reactor design and its systems and its inherent safety functions, preventing security incidents or anything safety incidents, to not allow that fuel to even conceptually be used or taken or anything like that. And another point is the differences, one of the main differences between the previous naval nuclear reactors that we've seen, in order to make them so small to fit in submarines and other battle warships, they had to use high enriched uranium, which is very much controlled and is one of the main reasons we don't even go into that realm of naval nuclear reactors. For these advanced reactors, they're using lower enriched uranium, they're using HALEU, they're using fuels that is much more difficult to proliferate.
Weaponize, yeah.
That's right, yeah. So that's my point is, if we can engineer these safety and security into the systems, into the ship and in the reactor before the situation even comes up, we'll have inherent safety functions. And Giannis's design has a great example of how that happens, but other designs have probably other, systems addressing this specific concern. Yeah, thank you.
Great. Yeah, I guess some more questions for Giannis specifically. There's a few in here just about core power, and I'll start with this one, which says, have regulators affirmed that ambient pressure reactor designs will result in basically no emergency planning zone?
Yeah, I saw that question. I also saw a person asking questions, Steve from NewScale, which is one of the companies that got their framework for a reduced EPZ approved by the NRC a few months ago. So I think it ties very well to the question. We have someone from the audience. We are working with the regulators, and we know the framework that we need to take to prove that the reactor does not need an EPZ beyond the boundary. The framework to do that is by proving your reactor is safe enough in the case of the most severe accident. The dose outside of the boundary of the plant does not require emergencies below emergency thresholds. So to have that, one of the components that we believe after discussing with regulators is that to have ambient pressure, because if you have high pressure, then you have in the nuclear accident, you have the creation of a plume, dispersal of radioactive material. In the MCFR and shielded design, you never have dispersion of radioactive material. So that is one of the main components, but there is a framework to be followed as we work with the regulators and we provide evidence to them to finally have a licensed reactor in the next following years with an appropriately reduced EPZ. So there's not practically zero EPZ. It's an appropriately reduced EPZ that we prove to be, let's say, true. I don't know if that covers your question.
Yeah, that was good, or helpful, I think. So another important question that's coming up in a few different forms here is basically like business model, right? I mean, we all know that nuclear reactors are very expensive, but there must be some idea that maybe the costs net out over time. And so I don't know, maybe Arunava, if you'd be interested in replying to one of these. We have one question, for example, that says a nuclear powered vessel will be much more expensive than a conventional vessel. How will the ship owners pay for these? And then I think there was another one in here as well, which I'll get to, but you can start with that one. Actually, here, I'll share this one. How can costs of a nuclear powered ship be brought down to be competitive with current and future non-nuclear propulsion? Historically, nuclear is always much more expensive. I think you're on mute right now.
I can start if you'd like.
Yeah.
If I don't have this is not my expertise, but I've heard a bunch of, let's say, business models and theories around this. I think we believe that the most feasible one is that we have a very high capex, so the initial capital for the ship owner is very high because you have to invest in a nuclear vessel, but actually the OPEX, so the operating cost, is extremely lower. And if you factor in the carbon tax that is already happening and will happen, actually it is so cheaper that the nuclear option becomes feasible. And then we get way out of my expertise when we talk about some leasing models. I know there's some leasing opportunities. So basically we have the nuclear operator, which has the reactor and the nuclear material, and then the ship owner would lease the reactor from them in their ship in some sort of deal that benefits both, basically. I don't know if that starts to bring the ideas in for how we make this feasible. Arunava, would you like to add something, or Meg?
Yeah, another thing that happens is that as I mentioned earlier, the life cycle of a conventional ship is 20 years. But if you are putting if we are using a nuclear battery for propulsion, then with a little bit of design tweaking, we can have the life cycle of the vessel almost double, because there's not much maintenance to be done except for the normal hull and steel maintenance, right? So that would also be an advantage. But then yes, the cost is something that again probably the lease model would be more attractive to many shippers, because the huge capex is always going to be a discussion.
Yeah, and to touch upon that as well, Arunava, and I'm not a nuclear field expert, but with advanced designs, one of the big criteria that they're looking at meeting is manufacturability. And that means having a standard design that you will produce the same reactor over and over and over again, ideally, which should reduce the cost of manufacturing. And that's a severe impact on the capex of that original construction. So if you follow, maybe not now, but in the next 10 years, I believe next 10, 20 years, there'll be a big spike in this development of seeing these reactors getting that license for a standard design. And if we see that being put on a marine application, then that will probably help bring down capital costs as well.
Yes, and I think the 2020-year mark probably would be a more or less correct projection, because the existing existing ships today, they have to be phased out before these nuclear ships, propelled ships come in. So it would be a natural life cycle ending and the new vessels coming in. So probably that's when it'll all start falling in place.
Great. Another question here from Steve at NewScale, which I think is very important, is it says experience from the 1960s and 1970s, especially with the SS Otto Hahn and NS Mutsu, had shown considerable opposition by international ports for nuclear ships docking there. How can we prepare ports to accept nuclear shipping?
I think I can start on that, River, and it's a great question, and it's one of the big challenges and opportunities for advanced nuclear to jump upon at this time, because it's a question about perception. Understanding that in the 1960s and 1970s, there was still heavy opposition, and there still is today, about what nuclear power is and is not. So, and we see this in the U.S. Military fleets as well. Some nuclear powered vessels, even though they have government agreements with wherever they're going, wherever their destination is, some places they're still not allowed to enter, and that's based on the local regulations in that port and in that country. So that will be a challenge, and it's really a perception, a social understanding of the reactor. For the technology, it's why we're talking about reducing the EPZ. It was reducing the zone, the potential zone of impact and emergency in the case of a disaster of that reactor. Not to mention the inherent safety features that are going to be designed into the reactor itself. Still is going to have that EPZ, hopefully to reduce it. So in addition to talking about the technology, you know, we all understand what nuclear power means. For those who don't understand nuclear, for those who don't understand exactly what we're talking about, this is exactly this kind of session is why we need to talk about the technology is safer. The technology is being implemented and it will be checked and verified correctly. And this is what the social aspects, social perception needs to understand, right? The technology and the regulations are covering that. We are having fundamental goals for safety for these systems. So even though they haven't been built yet, our priority is safety. And a lot of that comes from perception and education.
Yeah, I definitely agree with what Meg said. I mean, the question hits it right on the dot. The port authorities is basically one of the trickiest subjects and problems that we have to tackle. But the nuclear industry is, I think, the most overregulated and statistically the safest industry, energy industry out there. So the only way that these reactors ever hit the water and are applied is only if they are extremely safe, competitive and reliable. And as Meg said, we are looking at accident scenarios and safety decades before these systems are constructed and they go critical. So they will be so safe that I believe that the public perception will slowly change with that. And at the end of the day, if we have probably reduced EPZ and we can go through canals and everything is okay, it is not the end of the world. I believe, this is my personal opinion, it's not the end of the world for some big ports to be prepared for emergency. So this is already happening in many countries with the nuclear submarines. The port that they go to, the people on the port know what to do in case of an emergency. It won't be a showstopper, in my opinion, if some ports decide to do that, but in general, we want ports and canals to not have to do it, and that's why we are advocating, we are designing extremely safe technology. Yeah.
Great. So there's another good question here in the chat that I'll try and provide some context for, because I think it's something we talk about a lot, at least Meg and I do in our work, because there's an interesting situation we have right now, right, where in the United States we're investing in the development of advanced reactors. But when it comes to the maritime industry, the United States is actually a pretty small player in terms of the actual vessels. Very few of the largest container ships, if any, really are flagged in the US. So the market is really outside of the US. And so figuring out how we address all these questions we've just been talking about international acceptance and all this, where you know, the market is far beyond our borders, I think is kind of an important consideration for thinking about the market and deployment. And so one question that just came in here, and I'd be curious to hear everyone's response, is how much influence can the US really have on maritime when it builds and operates very few commercial ships?
I think I can start, River, and I probably don't have a great answer for this, just as for reasons that you said. But I think the U.S. is in this position, and the DOE is taking this position, is my opinion, is because of the funds that I've seen be distributed for research into advanced reactors. Yes, other countries are also doing advanced reactor research and deployment, which is great. But the US specifically, if we're looking at what they can do, is really push that the technology forward. And it's important as we think about the applications and the end use of that technology to get everyone involved from the start. So this is important that the DOE is funding research into lots of types of reactor technologies, advanced reactor technologies, supporting it through their national lab systems, and we're integrating both stakeholders in the maritime and the nuclear realms. But like River said, there may not be many shipbuilding opportunities or much influence based on the US fleet, but there are so many vessels that visit the United States for merchant activities that we do have an influence on those vessels. We do have a say in what regulations they need to meet. The US Coast Guard inspects all vessels that come to US ports. So we are a big player in the maritime industry, right? The United States, we know that. So even though we might not have the biggest fleet, we have a big say in the nuclear, advanced nuclear technologies realm.
Yeah, from the core power perspective, I agree with Meg, of course, but from our perspective, we believe that this nuclear solution is so disruptive that some power like the US could take advantage of it and could actually be a great opportunity to increase exponentially its presence, its maritime presence. So we're talking about a disruptive solution that will give a very good edge to the people who adopt it first. And actually, we think it's a good opportunity for the US to have these types of vessels.
Excellent. So I want to get back a little bit to the technology because we have, or actually rather like the applications, because we have a couple questions in here that speak to basically how do you envision using a reactor on a ship, right? Is it going to be propulsion? Is it going to be is it going to be for other applications? And I think that's something we haven't really gotten into detail yet in our conversation. So I'll share a couple of questions, but I think what we should do is discuss a little bit more like what else is out there beyond propulsion, right? We're talking, a lot of the conversations have been focused on that because I think it's probably one of the most compelling use cases, but there's a lot of stuff out there. There's a lot of other ways to use this technology that I think are going to be just as important. And so I'll read two of these questions and then you all can kind of take it in what direction you want. But I think for the first one, it says, how does core power balance the efforts between the direct nuclear powered ship and the floating nuclear powered fuel production plant efforts? Or is there sufficient overlap that such balancing is not yet an issue? So there's that one. And then, where's our other one? Are nuclear vessel reactors envisioned as being used exclusively for vessel propulsion and support systems such as electricity? If using a small modular reactor-like approach, assuming power capacity may be in excess of what a typical vessel may need, does the power capacity of the conceptual reactors have potential for additional uses during a voyage? For example, using excess power to produce chemical products?
Yeah, both very good questions. I will start with the first one. So yeah, you are correct with your assumption. Basically, the propulsion is not direct, is electrical. So in both cases, in the ship and also the floating power plant, the heat from the reactor heats up a medium, either steam or supercritical CO2, and that goes into a turbine, and that creates electricity. So create electricity in both scenarios, basically. Now, the electricity in the ship can be used, also answering the second question at the same time, can be used for many applications. It can be used, of course, to propel the ship. It can be used to provide hotel load, is what we call all the other electrical need of the ship. It can be used to provide power to a port if needed. And then when it comes to the floating power plant, we can, of course, feed it to a chemical plant to produce electricity, but we can also deploy it to areas that need, for example, disaster relief. So we believe it's a great disaster relief solution. And also it can be implemented into the grid. It can act as a land power plant. with the added benefit of not being susceptible to earthquakes and not being susceptible to tsunamis, because these are deep sea floating power plants. So at deep sea, you don't have, of course, great tsunami height. You don't have a tsunami, basically. So yeah, you can find a lot of ways to use electricity, and on how we balance the two, let's say, two applications. I think depending on the depending on what we're asked to do, we consider both. I would say equally on some degree. I don't know if Meg has something to add to that, or in the terms of a classification point of view.
Oh, like I said in my presentation, we're not excluding any potential applications, right? We're willing and ambiguously looking at this technology from a class perspective, for safety perspective. If you want to use it in a novel, crazy, innovative way, as long as you do it safely, it should be fine, right? So we're not so concerned with is nuclear shipping or is nuclear floating power going to come first or whatnot. We have already seen first movers in the industry, right? We've seen for regulatory simplicity, I say simplicity, but it's just less complex than shipping, is stationary floating nuclear power. We've seen designs starting for that, and you can see it in the news. But there are the details of it are specific to every application. The power requirements, the thermal and electrical, the thermal electrical integration on board a ship or an offshore platform, those are very design specific. What is that vessel doing? What is the operating plant producing? How much for how long? What's the power requirements of that ship? Is it stationary for a long time? Are you wasting a lot of this energy, or is it constantly, back and forth across the Pacific? I can't answer the question because it's a very application specific that you need to do a lot of research for, and that's the subject of which we're already studying, right? How can we optimize the reactor? How can we control the reactor with various loads and integrated into ship and floating systems based on the demand that we ask of it?
Yeah, I'm curious, Arnav, if you have any thoughts about applications beyond just propulsion, and what you might see in the near term as we arrive at the propulsion, or hopefully arrive to propulsion.
Yeah. Okay. First, I mean, if it's something as extreme as a tsunami, we cannot be having anchored installation. So obviously these installations, I mean, if you look at around the US, you've got huge number of offshore platforms, right? I mean, this area is safe. Definitely a geographical location would be chosen for offshore production platform. The history of tsunami or such catastrophe occurring would be less, right? And if and in case of an installation where nuclear power is being used to produce green fuel, there the nuclear power can easily be redirected for propulsion as well. So you don't have to really be having a separate propulsion unit to get the platform from one position to a safer position, probably when there is a risk of any catastrophe. So that's part of it, and yeah.
Great. So I'm going to jump back a little bit to what we were talking about earlier. We have a big question here that I think is important to try and address, which is basically how we, again, almost all reactors today that are used at sea belong to navies, right? So what types, how do we draw a line between naval applications and commercial applications? And what type of steps can we take going forward to make sure that those are, very distinct in the development of a commercial nuclear maritime technology.
Can I answer this? I mean, there's one point here that I think Yanis had actually mentioned. It has to be the large container ships because they are the ones which guzzle the maximum fuel. I mean, even if you're comparing a large container ship and a large Valemax size bulk carrier like 380,000 deadweight or 400,000 deadweight bulk carrier. I mean, that bulk carrier does not consume even half the fuel that is being consumed by a large container ship. So probably the target tonnage would be the container ships first, and then smaller ships can still work on alternative green fuels.
Yeah, this is very close to our idea, and you will be happy to know that we actually have designs also for nuclear container ships. But yeah, this is our logic also. We don't need to make every single ship be nuclear. We just need to do that to those who contribute the most to carbon emissions, which are the largest vessels. And the rest can use, of course, green fuels and other solutions, scrubbers, etc. Yeah.
Okay. We just have two more questions in the chat. So to follow up on the regulatory question, does the Nuclear Regulatory Commission or other national nuclear regulators also have purview to oversee maritime nuclear applications? Do they have existing regulations for these types of applications?
Yeah, I can follow up with that, River. That's a good question. I might not have clarified clearly previously, but from a classification perspective, ships will be classed and offshore structures will be classed to a society according to the IMO. That's covering structures, it's covering equipment, it's covering policies and the operations of those vessels. Other than requiring a vessel to prepare itself to receive a reactor and the subsystems on board, classification in the IMO does not cover the licensing of a reactor. So that will be done through the NRC, and the NRC doesn't have a lot of guidance for marine. I say that because they might, but I don't know about it because I'm not sure there are any. They're really focused on our land-based applications. The NRC is. They're aware of the potential maritime applications, and so is other regulatory bodies. But everyone has a specific part to play, right? Where the NRC or some nuclear regulator and licensor will be covering that specific technology, and marine regulators will be covering the vessel and the platform for which it is installed on. So that's why it is complex. These systems, especially when you start talking about the integration of these systems, auxiliary systems on board are marine systems being fed by nuclear power. That's kind of a gray line where we need to see what the gaps are, and we need to work closely together, the maritime regulators with nuclear regulators. And I'm not just talking about the licensors. I think this was mentioned in a previous comment, but also the transport of nuclear material, right? The marine industry has some regulations for ships carrying nuclear waste, nuclear fuel, and other nuclear material, but never as a fuel to be used on board that specific vessel. So there are some gaps that we're seeing, and those are currently being discussed and investigated right now. So I hope that clarified kind of the understanding of regulations there for that question.
Yep, thank you. And the last question we have here is about ports. So what additional security measures will be required at the ports?
Ideally, none.
Yeah, ideally none.
The idea for especially advanced technology is we want minimal change to the ports themselves. That would be the biggest resistance that we would see. The communities should, like I said earlier, should be aware and know that there's maybe a reactor in their port, but there's nothing that they should have to worry about because the technology should be inherently safe. And then we've already thought about the potential risks and the potential disasters. So ideally none. I don't know if Jonas has more to add to that.
Yeah, I mean, yeah, I agree with you. The most fundamental ones would be just to know in case of an emergency, how to evacuate, how to shelter, and then to have some iodine tablets that you can take to protect your thyroid. Although with ambient pressure reactors, as I said, there's no formation of plume, there's no expulsion of iodine, the dangerous isotope of iodine, that can get into your thyroid. So that comes back to your point of this technology is so safe that we have to, the people in the port don't have to be as worried as they would be if a nuclear submarine with a PWR was on board, which is PWR is a great and very safe machine. I want to make this very straight, of course.
Yeah, and one more thing, if I could elaborate, but when I say ports know that a vessel is coming in, it will likely be required that there's a safety risk assessment done for that vessel, even if its EPZ is very small. They're extra careful about, and exactly why we have received these questions. We're concerned about this, and we will be doing risk assessments and safety evaluations, and safety procedures will be most likely required to be in place for this visiting and departing vessel to port. And we've seen that from the history of the Savannah in the 60s, every single port that she visited, there was an enormous document for safety procedures for that vessel to enter and to depart and considerations for emergency. Well, I don't think that the EPZ or those specific emergency situations that the Savannah may have posed to ports will be the same for future vessels or future applications. I see some of that is going to translate into future port accesses. We need agreements and agreed procedures in places, which will take a bit more work. But ideally, from an optimistic point of view, like I said, no additional safety measures should be necessary.
Excellent. That was our last question. I think we're going to be able to finish on time. I just wanted to say thank you to all of our presenters. Thank you to the audience, to everyone who attended and shared all these excellent questions with us. I really enjoy this conversation. It's been exciting to work on this topic, and I'm looking forward to keeping everyone updated. You can follow our developments on this work. NRIC has it's NRIC. Is it nric.inl.gov/maritime if you want to learn more about some of our efforts. And then each of the organizations that our presenters represent are doing work in this space. So feel free to reach out to us with any more questions, and have an excellent rest of your day. Thank you.